What is up, guys? Welcome to another episode of CCT. So today we are going to go over a super important concept for all interviews and just computer science in general. Some of you may think you already know what binary search is. I'm sure you do. But I'd like to teach you it on a very fundamental level. Teach you it so that you really understand what's going on and that there are no guessing. In fact, I only recently sat down to fully understand how binary search works, especially with the off by ones. You know, when you have binary search, I see some people, like, you have an array like this. I see some people have start here and end here, but sometimes they have end pointing here at the start. I've seen in the while condition, I've seen start is less than end. I've seen start is less than or equal to end. I've seen then to calculate the midpoint. I've seen start plus end divided by 2. I've seen plus 1 here sometimes. Plus 1. Okay, that's an ugly plus 1. So basically, for me, am I just supposed to memorize it? Are there some combinations that work? Like maybe if I put the end here and then I have the plus 1 here and then I do less than, does that work to find the midpoint? And so you're either forced to memorize one of the combinations or fail miserably trying to go through all the edge cases in your head. Or you actually understand these things on a fundamental level. This episode of CCT is going to go through this in depth and a lot of variations of binary search, which are just really important to understand, and you'll be able to conquer any binary search problem in the future if you watch those through the rest of the video. Okay, so let me label this as the 3 confusing parts of binary search. You have what to put the start and end. Let me write this out a little bit more programmatically. So we have start gets 0, end gets length. This is pseudocode. I'm going to do -1. I'll show you the one that I use consistently. That's not the only one, and I'll explain what the other ones are doing. I do have a less than or equal to here, and then my mid gets start plus end divided by 2. Okay, so these are the 3 confusing parts. Then the rest is like, oh, if like the array at mid equals the target, yay, you're done. And if it's less than the target, then then start goes to mid plus 1. I mean, that part's easy, and that part I'm not going to go over. This is a video to deeply understand binary search, not just the concept of, oh, you split it in half. If it's bigger, then you move the end one to the left of the middle or whatever. Okay. So let's start with the start and end. Does it matter if it's length or length -1? I will strongly recommend length -1 here, because if you do have it pointing to the length here, and let's say your mid is greater, your target value is greater than all of these values, the you'll eventually get to like the start pointing all the way over here, and the mid still point, or the end still points here, and then you'll eventually get to the, and if you're not checking to make sure you don't go out of bounds, then the start can, or then the mid can point here, or the start can point here, and then the mid goes here, and then you check this value. Basically, there's a lot of extra complexity that you have to think of with going out of bounds if you start end here. But if you start end here, then the mid or any of the indices that you check can never be out of range. So that's why I'm going to recommend it being here. It is possible to do it here, but you're just going to have to be slightly careful and make an extra check that your mid doesn't go out of range. Okay. Here's the next part. Start is less than or equal to end. Okay, let's go over some 3 cases. Let's say two cases. Start, end. Let's say we get up to here in the worst case scenario. Like we traversed a lot of this array through binary search. We cut it in half, then we cut it in half again, then we cut it in half, and we've just been getting really unlucky in our mid hitting the actual target, and we get to having 3 values left, right? The end is near. So so the mid is going to okay, wait, actually let's draw this case as the these are the 2 like ending cases, and I want to show you first that they both boil down to the same thing eventually. So this one, the mid's going to point here, and if it's less than it, then start and end are both going to be pointing here, and then mid's going to point here, and then if it's less than it, if it's greater than it, so if it's greater than it, then yeah, let's just say it's greater than it. So we're going to boil down to this case where it's start and end, and then the mid's going to be here. Okay, so if the mid's here, if it's less than it, then we know it can't be it. So then like end would be pointing here, and then we know that the number doesn't exist. If it's greater than it, then it boils, then start moves to here, and then we get to this again. So why is it important to do this check when start equals end? Well, here's something that I didn't realize, or I guess wasn't so obvious to me. It's the fact that start and end have really no meaning. They have meaning, but we're never really checking. We're never checking the start and end. We're only checking the value at the midpoint. So let's say start is here and end is here, and let's say the target is at start. Let's say the target is at end. The only way we could get the mid to check at this point here is if start equals end. Because if start is just one before it, the mid is still going to point to start because we're rounding down with this mid. So the only way we could actually check this target value is if start equals end. That's one reason to remember why it has to be less than or equal to. Why I had a slight reservation when I said if the target is here, then the mid will never point to it, if we don't let start and end equal each other is because it's possible to have a situation like this where there's two of them, and then the mid does end up pointing at the start because we round down and the middle is here. But it's actually impossible for the mid to ever point to end if we don't allow this here, because we're always rounding down, and if we don't have this, then this is the closest we can get. This is the closest iteration we can get when start is pointing here and end is pointing here. And then mid would go here because that's the average, and whatever would be less than it, so start would move up here, but then we can't check this to be the mid. So in order to allow us to check for the end, and also sometimes you can't even check the start value, we need the less than or equal to. Remember, the start and end values are not checked. They are still, this and this are still candidates to be the target. And the only way to actually check them are if they are pointing to the same thing. That is why we need this less than or equal to. Less than won't work. Okay, let's get to the mid. This is a rounding down mid. There are ways to round up with the +1. That is perfectly fine. I just think it's kind of a preference. People always just round down, I guess. It's just a habit, I guess. Because like here, I just automatically put the mid in here because I knew it would be there. I knew it's the lesser of the two when it's even. So I would just pick either... I would just pick the rounding down. That's what everyone does. Okay. But I just want to highlight one more time about point 2, why it's less than or equal to. The start and end are not special. They are still candidates. They are it's a closed boundary, and we need this less than or equal to in order to check the start and end boundaries if it gets to that point. If it gets to a point like this. Right, because if we didn't have that, if it was just less than, then when we get to this point, and let's say the target, let's say it's 7, 8, 9, and our target is 9, then we would say, oh, it's greater than 8, so that means, or 9 is, the target's greater than what the mid's pointing to, so then let's move this here. And remember, the start and end are still candidates. We need to check this when they're equal to each other. I want to quickly go over this one again. So let's say it's let's say it's 10 and 11, and then the mid's pointing here. Well, we already know, we guaranteed it's not here, so it's not in here. And if our mid's pointing to 10 and end needs to come to the left of mid here, that's a problem. Then we know that it doesn't exist, so that's why if like end is actually less than start, that's a problem. That's a problem. That's when we know it doesn't exist. All right, cool. I hope that was informative. Let's move on to the variations of binary search. Please try to watch this again and think about it yourself of why you should use these 3 checks in your binary search. Let's change colors. Let's say I have an array like this. And instead of telling you the numbers in the array, I'm just going to tell you if it's to the left or right of any number that you pick. Okay? So, yeah, how would you do it? And you might think, well, this is just like binary search, and you're right. But I want you to pay very close attention that you do not need to know any number except your midpoint number. So binary search, you're like, okay, start, we already discussed, this is where we're going to put the start and end. Midpoint is here. And you ask me, you say, hey, is it to the left or right of this number, or does it equal this number? And I tell you it's less than this number. Then what do? Where is your next midpoint guess? Well, you might think, okay, so we know it's less than this number, so maybe we could just move the end here and then guess the midpoint here. And please keep this in your head. This end and start are just for you. It's really just for you to be convenient and remember the start and end. These were never checked, and we don't care about their values. We don't care. The only reason we have these here is so that we can pick a nice midpoint here and do this logarithmically. So remember, you're only asking me one question in this. You don't care what the start and end is. You just care what this midpoint is. And then you ask me, is it greater than or less than or equal to this number? And I tell you, okay, it's greater than this number. So then you think, okay, if it's greater than this number, like I really want to show you how insignificant this start and end is, and how much it's really only for you for you to store things conveniently and narrow it down. Because really, if I just stored that, oh, I know that it was less than here and greater than here, then I know it's somewhere in here and I could do something to find that. But instead of just remembering that, I put the end index here and then I put the start index here. Again, it's just convenience. I'm really trying to think of how I could explain this better. You do not care about the start and end values. They are just a way to move boundaries. Okay, so then you guess here, and that's your midpoint, and I say, oh, it's less than that. Okay, so then start and end are now pointing to the same thing. And because we have the less than or equal to check, you will put the mid smack dab in the center, and you ask, you ask me, is this less than or equal to or greater than the target? And I say, let's say I say it's equal to it. Great, you found it. Return the index. Let's say I said it's less than it. Okay, end is going to move to 1 past here, and that's a problem. Or sorry, it's greater than it, so it moves to there. And that's a problem, because now end is less than and start. And let's say I said it was less than it, then the start would move here, so that means start is greater than end. And that is also a problem. Okay, so remember, the key thing to take away from this black box binary search example is that you only needed to ask me what this midpoint value was, what the mid value was. And you just use start and end to conveniently narrow things down within an array. Cool. Let's move on to the next example. Let's make this a little harder. Let's say I gave you an array that was sorted and pivoted. So 6, 7, 8, 2, 3, 5. Okay, so it's sorted but pivoted, and I'll tell you it was shifted 1, 2, 3. I'll tell you it was shifted 3 spots to the right. Okay, how would you find, with binary search, how would you find a target value, for example? And you should probably pause the video to think about this, I think. Okay, this is tricky because we're going to use that black box idea again. So if I told you it was shifted 3, maybe you could think, okay, one thing I could do is just like take this part of the array and put it over here somehow, and then 2, 3, 5, 6, 7, 8, and then do a regular binary search with this. Fine, but there's a way to do it without using that extra memory and time to resort it like this. You could instead use a black box. Oops. I'll keep that here. Whoops. How can you use a black box? Let's say I have this here. You have start here. You have end here. These technically correlate to start being here and end being here. And start is 0 and end is the length of this minus 1. So you might be thinking, wait, hold on, this makes no sense. Are you trying to tell me that start is pointing to this and end is pointing to this? Nope, that's not what I'm saying. That's not what I'm saying. Imagine this is, let's draw this in black. This is a black box. Black box. And you can ask me a question. You could ask me the question, you could take a midpoint, so let's just get the mid here, which would be index 2, for example, index 2, so this is where the mid is. And you could ask me, is the value here in the midpoint greater than, equal to, or less than the target value? And I have a way of figuring out the midpoint. I have a way of figuring out the value and giving you the answer. How do I find the value of the index at 2? Well, what I could do is I could shift it over 3, and then mod by length. And then look at the value in here. That will give me the correlating mid value. Okay, because I know, so for example, if it's 2 plus 3 mod 6, it's 5. So that means the midpoint is 0, 1, 2, 3, 4, 5. It's right here, and that's the value that I can put in here and tell you, okay, 5. So 5 is greater than, less than, whatever. Yeah. So how do I explain this? Black box 5. So there's obviously a mapping from like 2 to this, 3, this. And instead of me computing all of them, just like the black box, I'm only going to ask for a specific value of this original array. So maybe it's better to visualize it here. This is like the start, and this is the end here, right? Just like, and then they're pointing to start, and this is pointing to the end here. Okay? And I'm asking for the midpoint here, and I don't know the value because this is the black box. So in order to compute it, I have a way of finding the value by computing the index 2 turns to the index 5 of here, and then I could find the value of it. So I'm only concerned with this value, and then I say, okay, if I'm looking for 3, for example, it's too big, so then I move end all the way to index 1 here. So end is now here. And so again, then I ask the question, and then I find the mid, so now mid's pointing here. Great, and then I ask, okay, what is the value here at 0? And just like this magic box here, I can get the answer by figuring out, okay, the 0th index here correlates to, let's see, 0 plus 3 mod 6 for the length. That'll get me 0, 1, 2, 3. Oh, it's the value 2. And I can give you the answer, oh, the target's greater than that, so move S over here. So basically the point is I was able to make a black box that correlated to I was able to make a black box which represented the unpivoted sorted array, and then I was able to, instead of actually unsorting or reshifting everything, I could just ask the question. I was just able to ask the question, what is the midpoint, and is it greater than or equal to, and then just shift it, and then just move the starting or ending value. Okay, let's go to the last problem that I thought of. Let's get a 2D array. Six, 7, 8, 9, and it's in increasing order. Tell me if the target, like X is in there. How do you do that? Well, one thing you could do is you could imagine you have a start and end, where start is pointing to here, and end is the index of n times m minus 1, right? And then you could pick a value in here. This is the index, right? This is the index. And I'm asking here, what is the value of this index here? And this has to have some mapping here. And we could get that mapping just by doing some modular arithmetic, but then we get here. And I say it's less than that. So that means that the end points here. And then again, you find this index, you check this index. So it's all about finding the mid's index. And then after you find this mid's index, you find what the actual value is by going through your black box. Okay? That is a common theme throughout these binary search problems. You figure out a way to have a start at the beginning, some start and some end here, and you find you get this mid-index, and you figure out what this correlating value is in whatever problem you have. So for example here, we had a start and an end where the end was the length of it, and we were able to pick a midpoint of like have an index 2, and then correlate that 2 to the actual second value of the unsorted of the sorted unpivoted array. We were able to correlate it to this original 5. Okay, so that's the theme with binary search. Think of it as, remember, the start and end are unimportant. The only time you check them are because when start and end equal each other and then mid happens to land on them, or when start and end are one apart and then mid lands on the start, whatever. And the second thing is to always think of things as when you have a complicated binary search problem, always think of it as a black box where you have a start and the end. You have to cleverly come up with the values. Here it was n times m minus 1. Here it was the length of this shifted array. Then once you get it in this form, you get the middle index just like always. And then the next hard part is figuring out what this index correlates to. What value does it correlate to? Like, what value does this correlate to? You're going to have to go whoop, 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 and then you get here. All right, that's a lot to digest. Go over these problems again with binary search, and as usual, if you have any requests, feel free to drop them in the comments. All right, see you next time.